Welcome. Let me start off today's class by recapitulating what we have been doing. We have considered a universe which is filled with a variety of components, each of which has a density rho I. So, I here refers to the different components, and we have allowed for the possibility that these components also exert pressure. So, the pressure of the ith component is a constant Wi into c squared. So, we have allowed for the possibility that the universe has different components which fill it, and each such component is labeled by I, different components are labeled by I, and each of them has a density rho and a pressure P, which are related through some Wi. And then we worked out, with the expansion of the universe, how does the density change. That is the thing that we worked out in the last class, and we found that with the expansion of the universe, the density evolves as rho I. So, for the ith component, the density evolves as rho I a to the power minus 3 1 plus Wi is equal to rho I naught into a naught to the same power, but we have assumed that the scale factor at present has a value 1. So, essentially the density of the ith component into a to the power minus 3 into 1 plus W is a constant. Rho I naught is the present density of the ith component. Okay. So, the scaling behavior with the expansion of the universe depends on the value of the pressure, how the pressure is related to the density, and this is something we worked out in the last class. If there is no pressure, then the there should not be a minus sign here, it should be a plus sign. There is no minus sign here. So, as the scale factor increases, the density falls, and if it is matter, the usual dust with no pressure, then the density into a cube is a constant. If there is a pressure, then you can think of it as the material does work on the expansion, in the expansion of the universe, which modifies the behavior. You have to then look at the first law of thermodynamics and apply the conservation of energy, from where we are led to this behavior of the density as the universe expands. So, these were the two things that we did right in the beginning of the last class. The other thing is that we represented the present value of the density of any of these constituents using the density parameter, the value of the density parameter at present. So, the density of any component was parameterized like this, and this is the ratio of the density of that particular component to the critical density of the universe at present. Okay. So, we modeled, this was the basic idea that we had, that the universe can have different components. Each component is the contribution from each the present contribution from each component is parameterized by its density parameter. Once you know the present contribution, you can work out the contribution at any redshift, any value of the scale factor using this. Okay. So, this tells us how the density evolves with the expansion of the universe. Then we use this to determine the dynamics of the universe. Let me remind you again, we determined the equation governing the dynamics of the universe by just considering the equation of motion of any galaxy at a distance r. The force acting on this is due to the mass inside, which gives rise to this equation for the scale factor if the constituent of the universe has pressure, this has to be modified, rho has to be replaced by rho plus 3p by c square. So this is the equation that governs the acceleration or deacceleration of the universe. This is the equation that governs the dynamics of the expanding universe. So let me write down the equation. The equation is A double dot is equal to minus 4/3 pi g then into A into the contribution from all the components in the universe. Each component contributes 1 plus 3 Wi into the density, right, because I told you if the constituent has pressure, if the particular component has pressure, then the density has to be replaced by 3 rho plus 3p by c square. This comes from Einstein's theory of general relativity. Okay, so this is the equation that governs the acceleration or the dynamics of the universe, and this equation can also be written in terms of the density parameter at present for these different components. So all that you have to do is replace the density at, this is the density at any arbitrary epoch, these are all functions of time, scale factor is a function of time, density is a function of time. You have to replace the density in terms of the present density of that component and the appropriate power of A. Once you do this, then the equation that you have is A double dot is equal to minus h naught square by 2 where we have used the fact that the critical density, the present value of the critical density is 3 h naught square by 8 pi g. So we have used this over here to replace 4 pi g by 3. Okay, so we have the ratio of the density to the critical density at present, and you can use that, you can use this and you will get this relation. Okay, so this is essentially the equation that governs the dynamics of the scale factor. Next, we integrated this equation, we multiplied it with A dot and integrated this equation, or equivalently these equations are same, there is no difference. Okay, we integrated this equation, and let me again remind you, after we integrated this equation we obtained the following equation: A dot by A square, this is the Hubble parameter square, is equal to h naught square, let me not write h naught square here. So we integrated this equation and what we got was this is equal to 8 by 3 pi g into sum of the different densities plus a constant of integration which was 2e by a square. Okay, so this is the integral, first integral of this equation, multiplied with A dot, use the fact that we know the time dependence of rho for each component, and you can integrate this equation once, you will be led to this. We have done this exercise. And this can also be written in the following way: h square t is equal to, this is the Hubble parameter squared, is equal to h naught square. Again we have replaced 8/3 pi g by 3 in terms of h naught squared and the critical density, sum of all the components in the universe, the corresponding density parameter omega I naught, into a to the power minus 3 1 plus Wi. In this process we have also included this. So what have we done? We have also included this term 2e by a square as a fictitious constituent of the universe. So 2e by a square, we have represented this as a fictitious constituent of the universe This term actually corresponds to the curvature of the universe, spatial curvature, and we are here representing it as a fictitious density. And as the universe expands, this density should fall as 1 by a square. So this fictitious density, so we have introduced a fictitious density by hand, and this fictitious density that we have introduced, let me put it here, this fictitious density that we have introduced, you can see that you want this to scale as a square as the universe expands, so the W should be minus 1/3. Okay, so we have introduced this constant of integration, we have represented by a fictitious density called omega k, which has Wk equal to minus 1/3. Okay, this is introduced as a fictitious density. It is not really a density, it is a constant of integration, which is Einstein's theory can be associated with the spatial curvature. Okay, so that has gone into this already, into this. So this term has been put inside here. So this term has also been written as h naught square omega curvature naught a minus 2. Right, this term falls as a minus 2. So this term also, the contribution here in this equation is h naught square omega curvature naught a minus 2. Okay, this basically parameterizes this constant of integration. With this, now this is the entire equation, the first integral of the equation that governs the dynamics. Okay, now if you take this equation and look at it at present, you are led to the relation that h naught square is equal to h naught square into this, which essentially tells us that at present this term must be 1. Okay, so we have the sum of all the different omega I naught should be equal to 1. Okay. And this is true because we have also accounted for this constant of integration inside this by introducing a fictitious omega curvature corresponding to this. Okay, so this is the equation, these are the two equations that we discussed in the last class, and this is the equation that we finally use in much of cosmology to study the expansion of the universe. Okay, and the cosmological models that we shall be dealing with mainly has 3 components, 4 components. In addition to curvature is one of them, one of the possibilities. There are other 3 components, let me introduce those. The first one was dust, which has no pressure So this is ordinary matter basically, no pressure. So for this A cube then we had the relativistic particles. For example, the cosmic microwave background radiation, photons. There are other relativistic particles also possible which we shall learn about later. So let us write all of them as so for these particles omega r relativistic particles, for example CMBR. Photons are relativistic particles, isotropically distributed relativistic particles. This pressure is 1/3 rho c square and rho relativistic a to the power 4 is equal to rho relativistic naught. Then we also talked about the dark energy. And there is evidence that such a thing exists. The dark energy, of which the cosmological constant is an example, is a possibility, cosmological constant. This is something for which I represent it by lambda in general. Okay. So we are going to particularly focus on the cosmological constant. There are other possibilities also which go under the generic name of dark energy. Okay. So we are going to talk about cosmological constant which is represented by lambda. This is a constituent of the universe whose pressure is minus rho c square. Okay, that's all. That's basically by and large all that we know about it. So for this, rho lambda is equal to rho lambda naught. In addition, we have the curvature, which is not a real component. It is the way that we have introduced this constant of integration in this equation. So let us briefly just look at the solutions. Okay. So let us, before we look at the solutions, let us look at the behavior of the right hand side of this equation in a situation where we have a combination of all these terms. And we have the curvature also. Okay, let me put the curvature here on the same paper. For curvature, this is equal to minus 1/3 and rho curvature a square is a constant. Okay. Now let us consider briefly the possibility that our universe has a combination of all four of these. Okay, so the equation that governs the expansion of our universe is essentially this, and it has a combination of all four of these. Okay, so let us look at and try to get a feel for what the general behavior is going to be when I have a combination of all four of these. Let me make a plot of the density, the contribution to the density in each of these components as a function of the scale factor. And let me make the plot in the log scale. So this is log rho, this is log A. Okay. So as the universe expands, you are going to a larger and larger scale factor, the density is going to fall. For relativistic particles, for dust, for ordinary matter, the density will fall as a to the power 3. Okay. For relativistic particles like the CMBR, the density will fall as a to the power 4. So this is going to fall the steepest of all the components. So of all the components, the contribution from the relativistic particles will fall the steepest. Okay, this is relativistic particles R, and this will have a slope on the log plot. It will have a slope of minus 4. Okay, next the matter, as the universe expands, the matter density will fall as a to the power minus 3. So that will be something like this, possibly. Okay. And let us look at the cosmological constant. The cosmological constant will have a constant density, so that will be somewhere like this, lambda. This is matter. And if you consider the curvature, if you have a combination of all four of these, the curvature will fall somewhere intermediate to the matter and the cosmological constant. So you can see the lesson that we learn from this is that in the early universe, when the scale factor is very small, the universe is going to be dominated by relativistic particles, radiation dominated. It is going to be radiation dominated. Okay, and then you are going to have a transition to a matter dominated universe. And if you had curvature, then you would have a curvature dominated universe, and finally if there is a cosmological constant, you would have a cosmological constant dominated universe. If you do not have these things, then the question does not arise. Okay. So in general you will have a radiation dominated universe to start with, relativistic particles, then you will have a matter dominated universe. Then if curvature is there, you will have a, we know that radiation and matter both exist. If you have a curvature dominated universe, if you have a curvature component, then the curvature will dominate, and finally you will have a cosmological constant. If this exists, then it will be the final thing that dominates the universe. Okay, these two we know definitely for sure that they exist, because we have measured the CMBR and we see matter around us. Okay, curvature we do not know. Cosmological constant, there is evidence that this is very small if it exists at all, and there is evidence that there is a cosmological constant, whatever. Okay, the behavior chronologically is going to be like this. The early universe will be dominated by radiation, and the late universe, if there is cosmological constant, it will dominate. If not, it will be continue to be matter dominated. Simplest model, you only have these two, radiation and matter. So you have early universe radiation and later on matter. Okay, so if you have only two components, radiation and matter, then the evolution, early in the universe the radiation dominates, later on the matter dominates. The transition between these two is determined by the value of omega matter and omega radiation, relativistic particles. Okay, this is the broad behavior. Let us now, to get a picture of what happens, let us work out, let me briefly tell you how do you determine the scale factor. In a general situation, how do you determine the scale factor as a function of time from this equation? So if you look at this equation, this is basically h as a function of a squared. H is basically a function of a. The time dependence comes through a, the scale factor in these models. Okay, so we have the dynamics of the equation, we have integrated it once, and the final equation that we obtain is 1 by a square dA dt square is equal to h square a, where h square a is a known function depending on the different constituents on the universe, depending on the values of the different omega i's. It is a known function. Okay, so this is the equation that you have to integrate, and this equation is easy to integrate. So the integral of this equation is that dt is equal to, so I can take this onto the what I have to do is I have to take this onto the right hand side, bring this in the denominator. So this is equal to dA by a HA. So if you want to solve for the scale factor at any instant of time, you have to essentially do this integral 0 to a dA prime a prime h a prime, and there will be a constant of integration which we set to 0, because we would like the Big Bang to occur when t is equal to 0. Okay, so to determine a as a function of time, essentially what you have to do is you have to integrate this. This will give you t as a function in terms of a. You have to invert this to get a as a function of t. Okay. This equation also gives you the age of the universe for any value of the scale factor, and the present age of the universe, let me put it here, can be determined from this equation. T naught is equal to 0, the present value of the scale factor is 1, so this can also be used to calculate the present age of the universe. You have to just do this integral from 0 to 1. So if in your model you know all the different density constituents, what are their contribution at present, you can determine everything about the model. Not only can you determine the expansion history of the universe, how a behaves as a function of time, you can also determine the present age of the universe. Okay. Let us quickly work out very simple models. In general, you can do this numerically, put this in a computer and use some simple rule like Simpson's 1/3 rule or something like that to do this integration numerically. It is very straightforward. Okay, that will give you t as a function of a, you can invert that. Let us do a few situations which are simple to get an idea of what happens. So we have learned that early in the universe is going to be radiation dominated. So let us look at the behavior in a situation where the matter, cosmological constant, curvature, all can be neglected. So suppose we are looking at the behavior of the universe somewhere in this regime, where the radiation is the most dominant thing, everything else makes a very insignificant contribution early in the universe. Okay, so in such a situation, the equation that we have to solve, this is a radiation dominated universe, and the early universe we know is going to be radiation dominated, because the density of radiation of relativistic particles will increase as a to the power minus 4 if I go back in time. Okay, so let us look at the behavior of this equation under that condition. So we have to basically do this integral, where h a prime, now let us put the form of h a prime for a radiation dominated universe. I will have only the omega radiation naught a to the power minus 4. Okay, so the integral that I have to do is t is equal to 0 to a dA prime a prime. I have to put h a there, so this is going to be h naught square root of omega r naught a to the power minus 4, so minus 2. So I have a prime to the power minus 2 and 1 by h naught omega r naught. Okay, so we know what this integral is. This integral is a to the power, if I multiply these two, I will get a to the power minus 1, so which will be a prime on top. If I integrate this, I will get a prime square by 2. I will get a prime square by 2, at the limits I will get a square by 2. Okay, so this integral essentially gives me t is equal to 1 by h naught that is this integral. Okay, or you see that the scale factor a is equal to so the scale factor is 2 by h naught a is So, I will have 2 over there, 2 h naught, not 2 by h naught, 2 h naught omega r naught to the power half t to the power half. So, the crucial point is that for this model the scale factor is proportional to t to the power half, okay, and the age of the universe at any instant of time is a dot by a, sorry, the Hubble parameter at any instant of time a dot by a. So, for t to the power half, a dot by a is going to be half 1 by t, or t is equal to 1 by 2 h naught. Okay. So, this is the dynamics of the equation in a radiation dominated model. So, in the radiation dominated model the universe expands as t to the power half. Okay. Let me also remind you what it was for the matter dominated model. In the matter dominated universe, we have already worked it out. In a matter dominated universe, the expansion law is t to the power 2/3. So, you can do this, check that you recover the same thing again for the matter dominated universe. I will not go through it here. Okay. So, for a radiation dominated universe, the expansion is t to the power half. For a curvature dominated universe there is no gravity, so it is just proportional to t. So, we have already worked out what the expansion factor is for several of these models. So, we have now worked out what this is here. So, this is a t is proportional to t to the power half, a t proportional to t to the power 2/3, a t proportional to t in all of these models. Gravity causes the universe to slow down, the expansion to slow down. In this model there is no gravity. Let us look at a model with just the cosmological constant, which is the only one that we have not discussed as yet. So, in a model with a cosmological constant, the integral that we have to do, we have h naught h a. So, the cosmological constant, here the equation that you have to solve is a dot by a square is equal to h naught square omega lambda naught. For a cosmological constant there is no dependence of on the scale factor. This is the equation that you have to solve, and the solution to this equation is quite obvious. This equation can be written as, this has a solution that a of t is equal to e to the power some constant a naught, if you wish, e to the power h naught square root of lambda naught into t. It is an exponentially growing solution. So, for all of these other situations where gravity tends to slow down the expansion of the universe, we have power law solutions. For a freely expanding model it is proportional to t, whereas for the cosmological constant dominated model the expansion is an exponentially growing function of time. The scale factor is an exponentially growing function of time. Okay. And the value of the Hubble parameter h remains a constant, it does not change with time. So, and this universe has no singularity, it has a singularity at t equal to minus infinity, which basically means that there is no singularity, there is no Big Bang in this model. Okay, there is no Big Bang. It is an ever expanding universe with an exponential. Okay. So in general, okay, so this is this summarizes the general behavior in a model we have, where we have the universe dominated by radiation, dominated by matter, dominated by the curvature, and dominated by the cosmological constant. So if I have a universe where there is a combination of all of these, then in this phase of the universe it will expand as t to the power half. In the matter dominated phase it will expand as t to the power, let us take a simple model where there is matter, radiation, matter, and cosmological constant. In this model you will initially have a t to the power half, and then you will have t to the power 2/3 expansion, and finally you will go over to a phase where you will have an expansion which is exponential, okay, which is an accelerated expansion. It is not deaccelerating. The cosmological constant we have seen acts to, instead of slowing down the expansion, it acts to increase the universe, the acceleration of the expansion of the universe, which is acceleration. So the universe will then go over to a phase of accelerated expansion. Okay. So this is the kind of behavior which you have in a model where you have these three components, and in general, given this equation, all that you have to do, the equation that we have just worked out, is integrate this equation incorporating all the different components that we have. Okay. So I will give this to you as an assignment. Work out numerically the solution for a combination of matter, radiation, and the cosmological constant. Work out A of t. Take for example omega radiation naught to be of the order of 10 to the power minus 5, omega matter naught to be of the order of 0.3, and omega lambda naught to be of the order of 0.7. Okay. The total sum has to be 1. This is very close to 1. Work out the behavior of the scale factor as a function of time for a cosmological model where you have these three, h naught, rather h. So this is a homework. Please work out the expansion history for a model with this. Compare it with a model where instead of this you have omega curvature naught of the order of 0.7. The total sum has to be 1, right? So consider two different models, one where you have these three, another where you have these two and this. Compare the behavior of the expansion of the scale factor in both these models. So you have to determine okay, so plot the graphs and compare these models. Also determine the age of the universe, which I have told you how you have to determine, assuming h naught, h is 0.7. Okay. Now let me switch over to a different topic. So I have told you how to work out the dynamics, I have told you about the equations that govern the dynamics of the universe, and I have also told you how to work out solutions for these equations. We have worked out some simple examples. Let us now switch topics and look at the cosmological metric. Okay. So before we go into the discussion of the cosmological metric, I have to tell you a few things. So I hope we all know that in Einstein's theory, special theory of relativity, you have this very important quantity called the interval between events. Okay, so let me write down the expression for the line element or interval between events. Let me write down the expression here and I shall explain to you what it means briefly. x. Okay, this is how you calculate the line element or interval between two events. So in Einstein's theory of relativity, we have to think of space time rather than space itself. Okay, so we are dealing with a three-dimensional space with coordinates x, y, and z, Cartesian coordinate system, and there is time. Now the things that we are dealing with are events. What is an event? We all know what an event is. You are born, the clock ticks 1 second, that's an event. Okay, so we can represent events on what is called a space-time diagram. In a space-time diagram, we have the position of the event along the x-axis, and we have the time at which the event took place along the y-axis. And here we will only refer to one of the spatial coordinates x. Y and z are not being shown. Let us say that y and z do not change. Okay, instead of using time, we shall measure time in units of speed, the speed of light. Okay, so this is an event A. It is labeled by the place of the coordinate of the place where it occurred and the time instant at which it occurred. That is an event A. There is another event, let us say B, which in this diagram is vertically above A. Then let us calculate the interval for the event AB. The way you calculate the interval is you evaluate this expression for these two events. Now you see, for these two events they are not separated in space, in position, they are only separated in time. So for these two events, the interval delta s square is equal to c square delta t square. Okay, such events are said to be time-like. This is a time-like, these are two time-like, these events are time-like. Okay, and the delta s square is essentially c square into the time interval between these two events. So these two events, imagine a person sitting at one place and just sitting at one place. So this is at t equal to 0, this is t equal to 1. Time will just evolve for that person in a particular coordinate system. Okay. Similarly, let me take another event here and call it C. These two events AC, delta s square is basically negative minus delta x square. Just apply this formula. So for these two events, you see that the interval, this is called the interval. The interval is negative, it is the minus the length squared. Such two events are said to be space-like, and the value of the interval is essentially minus the distance between these two events squared. Now the utility of the event is apparent now when you consider something that travels at the speed of light. So imagine a photon being emitted from here and it travels at the speed of light. So after a time interval, this photon has reached here. This is the event D. So the photon is emitted here, and this is where it is, let us say, detected by a detector AD. Let us look at the separation AD. For the separation AD, you see it is traveling along the x axis delta x, and it is also evolving in time, so there is a delta t. Now since it is moving at the speed of light, delta x is equal to c delta t. So for these two events, which is basically the propagation of light from here to here, delta s square is equal to 0. Okay, these are said to be light-like or null. So along the propagation of light, the interval is 0, and the interval plays a very important role in special theory of relativity. Its value does not change even if I go to a moving frame of reference, etc., etc. Now this is briefly what is meant by an interval, and the same thing can also be written in spherical polar coordinate system. So let me write it here. If instead of using a Cartesian coordinate system, I can also use a spherical polar coordinate system, where this can be written as c square dt square minus dr square plus r square d theta square plus sine square theta d phi square. Okay. So, I have written the same thing in polar spherical coordinates. That is all, okay, which I am sure is familiar, this polar coordinates. Now, here we are looking not only at relativity, but we are also interested in Einstein's general theory of relativity. So, in the general theory of relativity, the gravity manifests itself as curvature of space time. So, this is the general theory of relativity. By the curvature of space time, how the way it manifests itself is essentially it modifies the way in which we calculate the interval corresponding to two events. It modifies the way in which we calculate the interval between two events. That is how the curvature of space time manifests itself in this. Okay, that is the first point that we have to understand. We have to accept, let us say that we will not bother to understand it here, we have to accept it that the curvature of space time manifests itself as that the way you have to calculate distances becomes different. And it is intuitively quite clear that if something is curved, the way you have to calculate distances is different from the way if it were you would calculate distances if it were flat. Okay, that is the main point. So, the question is, how do we calculate distances in this cosmological space time? So, what is this space time that we are interested in? We are interested in a cosmological space time, and the cosmological space time is one that satisfies the cosmological principle. The cosmological principle is that space is homogeneous and isotropic. Okay. So, if you have a space time where the space is homogeneous and isotropic, that is the cosmological principle. Not only is the density of matter isotropic and homogeneous, but the gravity it induces also is homogeneous and isotropic. Everything is homogeneous and isotropic. So, the space itself is homogeneous and isotropic. In such a space, the interval is calculated. Let me write down the formula, the way you would calculate the interval. The interval is calculated according to this formula. So, in such a space time you calculate the interval using this formula, which is very okay. This is the first thing. This is called the FRW metric, Friedman Robertson Walker metric. Okay. So, the metric is how what you use to calculate the distances between two coordinate points, and this is referred to as the FRW metric. This thing that we wrote down before is the flat Minkowski metric. Okay, this gets modified to this. That is the first thing for the homogeneous and isotropic universe. Okay. Now you see, one should not get very intimidated looking at this. It is not very difficult to understand. Let us first see what are the differences with what we are familiar with. So you should compare it with this. This is the space-time, this is the usual space-time interval written in spherical polar coordinates. The difference essentially lies in two things. There are two things which are different. One is this A of t, which is the familiar scale factor we have already encountered. That is the one difference. So A of t here is already familiar to us, it is the scale factor. So x here is the co-moving coordinate. So we are working in a co-moving coordinate, that is quite clear. Co-moving radius, x is the co-moving radius. Theta and phi are the usual angular coordinates, right. So it is just like this. Here you have the radius r, here you have the radius x. It is co-moving because the whole thing is multiplied by a factor of a square. A into x tells me the length, right. So this is the co-moving coordinate system. The whole length in this coordinate system gets multiplied with the function a square. Okay, if a is 1, then this looks exactly like this. There is one more difference, where the difference being I have this k. K is a constant which can have values -1, 0 and 1. This tells me whether if there is curvature. And 0 is no curvature. So if you set k equal to 0, you recover back exactly this. If you make the scale factor 1. Okay, so this is the spatial curvature, not the curvature of space-time. The space-time is curved already. Okay, this is the spatial curvature. Is the space curved? Forget about this part. See, this is just the space. Is the space curved? That is there in this factor k. L is the radius of curvature of the space. And it is co-moving because we are working in the co-moving length scale. So this is the co-moving radius of curvature. Okay, so let me bring today's lecture to a close over here. In the first part of today's lecture, we recapitulated the dynamics of the expanding universe, and then I told you the behavior in general, and also told you about the behavior for two particular new cases which we had not considered earlier, where we have a cosmological constant, and the other where we have only radiation. In the latter part of today's lecture, I introduced the cosmological metric. So this tells you how to calculate distances, time intervals in this expanding cosmological space-time. And I introduced the terms that you encounter in the metric, in this line element. In the next lecture, we shall look at this in more detail and understand what this really tells us.